Chapter 5 was called Building with Matter, and it was where we got a chance to look at the different properties that matter has, and we basically, in the first activity of the chapter, looked to see if matter was soluble or insoluble in water, meaning did it dissolve or not dissolve, and then if it did dissolve, did it conduct electricity? When we put the bulb inside with the two wires, did that matter complete the circuit or did it not? And then if it was insoluble, we looked at the same question. Did it conduct electricity as a solid or did it not conduct electricity? And we then used those conclusions to sort of sort the matter. And we saw that the things that were soluble and conducted were things that had formulas like NaCl and CuSO4 and CuCl2. The things that dissolved and did not conduct were things like C12H22O11 and C2H5OH. The things that were insoluble, did not dissolve, but conducted electricity as a solid were things that had formulas like Cu and Fe and Al. The things that did not dissolve and did not conduct had formulas like SiO2. And then basically what we did was we said that just by looking at these two properties, we classified matter into how the atoms or ions are held together, meaning the bonding that exists between them. So the things that were soluble and dissolved and conducted electricity when dissolved were all considered ionic substances, things that were bonded ionically. The things that dissolved but did not conduct electricity were considered covalent. The things that did not dissolve but conducted as a solid were considered metallic. They had metallic bonding. And then the things that were insoluble and did not conduct were considered network covalent substances. So you should be familiar with, if you were presented with a substance, you should be able to say whether or not it's going to dissolve in water or not, and then whether it's going to conduct electricity or not, based on the formula. And we're going to go through each of the different types of bonding. Now, ionic bonding, if we look at just the formula, we could recognize ionic bonding because you're going to see metal and you're going to see nonmetal. Metal, nonmetal. Metal, nonmetal, metal, nonmetal. And what it means for something to be ionically bonded is that metal atoms give up or lose their valence electrons to the nonmetal atoms. So here, these electrons were given up and they go to the nonmetal atoms. You then form positive cations, the things that lost electrons, negative ions for the things that gained, and you have this alternating array of positive and negative ions that attract to each other, and that's what holds those substances together. They dissolve in water, they conduct electricity when they dissolve, remember, because they have the moving ions. When an ionic compound is solid, it does not conduct electricity. It only conducts when dissolved. So only conducts when dissolved because the ions have to be split apart from one another. And the only way they would be split apart is if they're dissolved in water and the water molecules pull apart the positive from the negative ion. They are brittle solids, meaning they break easily, and then again made of metal and nonmetal ions combined. For the covalent substances, we'll do metallic, that's the next one in the chart. For metallic substances, which you're going to recognize because you're going to see they're all metals on the periodic table, their valence electrons are free to move about the substance. We said that we described it as a sea of mobile or delocalized electrons, meaning the electrons were free to move from this atom to this atom, and then it'll join this atom, and then it'll leave this atom, and then it'll go to this one, and you have all of their valence electrons moving throughout the entire sample, and that's what's acting as the glue holding all the metal atoms together. They do not dissolve in water. They do conduct electricity because of those moving electrons. They conduct as a solid. They're bendable, malleable, and they're made of metal atoms. That's what you should know for metallic bonding. For molecular covalent substances, you're going to recognize molecular covalent substances by looking at the formula here. You're going to see that there's only non-metal atoms. That's how you're going to recognize it. What does it mean for something to have molecular covalent bonding? Well, you're going to see there was molecular covalent and network covalent. Covalent means they are sharing electrons. Covalent, like valence, covalent, they are sharing the valence electrons between the atoms. Now, in molecular covalent bonding, they're sharing in groups. Sometimes it's 2 atoms, sometimes it's 3, 4, 5, but these individual groups or units are what we call molecules, and then each of those molecules are attracted to each other and hold the substance together. Some of these dissolve in water and some do not, and this was when we looked later in the year at the like dissolves like rule, right, for polarity. That's going to come up again in Unit 2. But if they do dissolve, whether they do or don't, they never conduct electricity because there's no charge to conduct electricity. They exist as solids, liquids, or gases, and they're made up of entirely non-metal atoms. Network covalent bonding. Again, the covalent means the atoms are sharing electrons, but this time they're not sharing in individual groups or units. The sharing is occurring throughout the entire sample. So one atom is sharing electrons with all the other atoms that surround it in a grid-like network, hence the name. These do not dissolve in water. They don't conduct electricity. They're extremely hard because the bonding is very strong because of that sharing throughout. They're made up of entirely non-metal and metalloid atoms, and there were 3 that we went over you should know is silicon dioxide, which is sand, silicon carbide, and the element silicon. Those are the 3 network covalent substances you should know. The last thing we looked at in this chapter was the idea of electrolysis and electroplating, right? The last thing we tried to do to see if we can make gold or harvest gold was, can you pull it out of a different compound? And we did a lab where we put nickel electrodes into a solution of copper 2 sulfate, and we saw that when we hooked it up to a battery, there were electrons that would flow from the negative end of the battery and would coat the nickel strip, and the copper ions plus 2 electrons that were in that solution would attract themselves to the negative electrons because this is a positive ion, these are negative. It would take those 2 negative electrons and it would actually turn back into copper 0, which means copper metal. And we saw that copper metal started to plate out on the strip. So we defined 2 terms. Electrolysis is the process of extracting a metal element from an ionic compound containing that metal. We dissolved copper sulfate in water, and then we extracted the copper out of it by force feeding it, basically, electrons to turn it back from an ion into an atom of pure copper metal. Another application of this, what we did, was electroplating. It uses electrolysis to coat a metal element on another surface. So basically what we did was, when we did the lab, the copper started to coat on the nickel strip. That was both extracting the copper out, the electrolysis, but the fact that the copper was coating on the nickel strip, and you can see the image here, that's electroplating, where you're plating one metal onto another. The most important thing that you have to remember is that whatever metal you are going to extract, like here, there's zinc ions in here. The zinc plus 2 ions need to turn into zinc metal again. How are we going to get it from a plus 2 charge ion to 0? Well, it has to gain electrons, and how many electrons is it going to gain to do that? 2. For the gold here, the gold ions that are in solution, if we want to extract that out as pure gold metal, right, the atoms are neutral. There is no charge. Well, we would have to give this thing electrons, and it would have to take in 3 of them so that its charge goes from plus 3 to plus 2 to plus 1 to eventually 0, making pure gold again, or extracting the pure gold out. That's where we ended with this chapter and this unit, and we really came to the conclusion that the only way to get gold, if we can't make it through nuclear reactions, would be to extract it from a compound that contains gold, and that process would be using electrolysis.